And welcome to this week's Crunch seminar. So this week we have two speakers again. Our first speaker is Professor Umair bin Waheed. He would be presenting on the topic titled Scientific Machine Learning for Geophysical Modeling Inversion. He is an assistant professor of geophysics at King Fahd University of Petroleum and Minerals. His research interests are broadly in the area of computational geosciences. Specifically, he is interested in automating and improving workflows through the use of smart algorithms for enhanced decision-making in subsurface energy systems. Professor Umair graduated from KAUST with a PhD in Earth Sciences and Engineering in 2015. Prior to joining this university in 2017, he was a postdoctoral fellow at the Department of Geosciences at Princeton University and a Writing in Science and Engineering fellow at the Princeton Writing Program. Without any further delay, please join me in welcoming Professor Umair Waheed. Professor Umair, you may want to share your screen and go ahead. Thank you.
Sure. Thank you, Somdata, for the introduction, and thank you for organizing and arranging the logistics of the talk. And thanks to George for inviting me. It's an absolute honor to be presenting to the Crunch group here and to talk about the different things we've been doing with the tools that you guys have developed over the years. So this talk will be about our efforts in using scientific machine learning, or specifically physics-informed neural networks, in the field of geophysical modeling and inversion. So the background of this talk is that about 2.5 years ago, I learned about pins for the first time, and I immediately, it looked like something that has a lot of potential for computational sciences. And therefore, I started devoting my time to it, and we managed to cover plenty of ground during this time, but our focus has been on solving problems that we face in computational geophysics. And I'll walk you through all the different things that we have developed so far and the impact pins have had in our discipline. And I'll also try to highlight some of the challenges that we face in the use of pins in, let's say, addressing those challenges in a holistic manner. So just to make sure everyone is on the same ground, so geophysics, as the name suggests, is the use of physics basically to study the Earth without digging it up. So essentially what geophysicists do is basically they try to look at the differences in properties in the Earth to build a geological map of what lies underneath our feet. And this is essentially what we as geophysicists are doing. So geophysics finds application in, let's say, many areas, primarily in oil and gas exploration. It's also used in earthquake hazard studies and in exploration of mineral deposits, but it also finds applications in other areas which might not be obvious, such as archaeology, and in studying and predicting volcanic eruptions. And it's also used in geotechnical site investigations, to name a few other applications. So the area of my personal research interests that I'm going to talk about today are basically two areas. One is computational, let's say, geophysics, in which we model and do inversion for seismic waves primarily, but you could also use some other forms of waves as well. So primarily my interest is in seismic modeling and inversion, and I'll talk about our efforts in using pins to address some of the long-standing challenges associated with seismic modeling and inversion. But also, my interest is in understanding and mitigating the risk associated with induced seismicity. So many of the industrial operations that are needed to sustain human society have the potential to cause earthquakes, which can be threatening in some cases. And therefore, it's of, let's say, high importance that we understand the subsurface processes, how these earthquakes are induced, and how to manage these industrial operations in a safe manner. And that's what I'm also going to talk about, and how pins can contribute to that domain of study as well. Okay, so the first thing that I'll talk today is about seismic travel time and wave field modeling. So the first thing that I'm going to talk about is the iconal equation, which is a nonlinear first order hyperbolic partial differential equation of the form shown here. So essentially what it says is that the arrival time surfaces or the gradient of the arrival time surfaces is inversely proportional to the velocity. So capital T is the travel time here, and V is your phase velocity. And this partial differential equation is subject to boundary condition, which says that the travel time at the source location is 0. So what we mean by source is, for example, if you have an earthquake, the place where this earthquake started, or the site of this rupture, for example, that caused this earthquake, is what we call the source in this case. So what the Eikonal equation does is, it's basically a high frequency approximation of the wave equation. It tells us the first arrival travel time associated with a moving wave front. So if you have an earthquake, let me just get a laser pointer. So if you have an earthquake here, then these waves will emanate outward towards the surface. And if you have this yellow receiver here on the surface, and you want to ascertain what would be the travel time of the first arriving wave at this yellow receiver, then it could be given by the Eikonal equation. So that's what we solve the Eikonal equation for. That is to get travel times associated with a propagating wavefront. Now, instead of using the original Eikonal equation, what we do use with physics-informed neural networks is what is called the factored Eikonal equation. So essentially, the idea is that instead of solving for t, we factor it into two factors. So one is called t0, which is the analytical solution corresponding to some homogeneous medium for which we know the analytical solution. And then tau is just now a scaling factor. So that is used to compensate or correct for the incorrect travel times as predicted by this analytical solution. So it's only the perturbations that remain, or the errors that remain in T0 compared to capital T. And when you plug this into the original Eikonal equation, it results in the factored Eikonal equation, which looks a little bit more complicated, but essentially all these terms, T sub 0 and its gradients are already known analytically, and we solve for this unknown factor called tau. And the reason why we do this, or why we use factored Eikonal equation, is for the following reason. So through our experience, we learned that when you're trying, neural networks prefer smooth solutions, or when your underlying function is smooth, neural networks can approximate it much better. So what happens is that the original travel time field has a point source singularity at the source location, which is here. And what you see here is the x and z axis. So this is depth, and this is the horizontal axis. And here is your source at the center with the travel time 0 condition, right? And then you have travel times increasing as we go away from the source, right? So T sub 0, which is the analytical solution corresponding to some homogeneous medium, captures this source singularity such that the solution that is left to be approximated is a smooth function. So this kind of function is much easier for a neural network to approximate compared to what we see in the first panel. So that's why we use the factored Eikonal equation throughout our formulations. So how would you go about using pins for solving the factored Eikonal equation? I assume the audience here has gone through many presentations on pins and understand how pins work. If not, I'll just quickly summarize what we do here. So we have a feed-forward neural network, as we show here. The inputs are, let's say here, x sub s, z sub s, which are the coordinates for some source location. And x, z are your training points from your computational domain. So essentially what you're trying to do is you're trying to approximate travel time from some source to some point in the computational domain. And you take different pairs and you collect a bunch of source points and collocation points within your computational domain so that you can sample the domain really well. And over those training points, you train this neural network using the underlying partial differential equation. So what would happen initially is that when you feed all of these, let's say, training points, it would give you some travel time that is absolutely garbage, and that does not satisfy the underlying Eikonal equation, but we force the solution, or we update the weights of the neural network by computing loss that is computed using the underlying partial differential equation, which is formed by the Eikonal residual term here. So this is the Eikonal residual term of the original, or the factored Eikonal equation. You have the boundary condition here. So essentially that's what you do, and you hope that at the end of this process, your neural network is able to approximate this function which maps the from between 2 points, so a source point and a receiver point you can consider, and it gives you the travel time. So it's able to learn this function. Now, typically in seismic exploration, we have thousands of sources, and you would get millions of source receiver pairs, right? And therefore, in what happens with existing, or let's say state-of-the-art methods or conventional techniques, is that you have to spend the same amount of effort for each new source position. Now, the good thing with pins is that once you have trained for, let's say, a representative number of sources, then you can compute the solution for the rest of the domain, because now it's able to approximate the entire field really well. And in our paper, we show that that it can save you time in the overall scheme of things. In terms of computational cost, it is faster than what you would do when you're working with the traditional methods, such as the fast sweeping or the fast marching method. So here is some results from our first paper on this topic, which we called PIN-IKE, in which we talked about solving the isotropic iconal equation, which I just showed to you. So this was published last year in Computers and Geosciences. So essentially, what we do is we have, for example, you have a velocity model, and here is your source location. What you're trying to do is you're trying to approximate the solution now using physics-informed neural networks, right? And here I show the travel time errors using fast sweeping method, where you see it's essentially something like based on the finite difference grid. So you see the errors because of that grid, which is increasing in the orthogonal direction of the grid. Whereas with pins, the errors are, let's say, more randomly distributed, and the errors are much less than what you would get with a first order fast sweeping method. Of course, you can improve the order of accuracy using a higher order stencil, but of course that would lead to higher cost. Whereas with pins, we have shown in our paper that you could compute the solution, and it performs faster than the first order fast sweeping method when you have a large number of sources. One more thing we talk about in our paper is about the use of transfer learning. So if each time you have a new velocity model, you don't need to randomly initialize your neural network. So if you had a velocity model that was very different, that's what we show, that we start with a very simple velocity model, we train our neural network, and then we use the trained weights, and we start our training process with new trained weights for a different velocity model. As we can see in this orange curve, that it converges much faster compared to if we were to randomly initialize the neural network. So this is one other advantage that is not available with conventional methods, where you cannot use the knowledge you have gained in solving one problem and use it in solving another problem. So that's a nice feature of pins that you could use. But also one thing.
Umair,
yes.
Can I ask you, this is interesting. So can you be a little more specific on the setup here? What is the new data? And is the data inside the distribution, I suppose, right? Can you describe a little more concretely the problem for the
okay, sure.
Yes.
Sure. Yeah. So so this is a modeling problem, and we don't have any observations or, let's say, solutions at any points here. We're just training based on a bunch of different, let's say, points in the domain and trying to satisfy the partial differential equation. That's the only setup. So you have, if I go back, so basically you have some points that are categorized as sources.
Yeah, I'm interested to hear how many sources and how many sources you had before, and how many new sources you have. Yeah.
Right. So the number of sources that you need essentially depends on the heterogeneity of your velocity model. So if you were to use for a homogeneous velocity model, then only a few sources were enough to approximate, the global solution. Whereas if you have sharp variations in your velocity model, you need more, let's say, sampling points. So there is no fixed number, I'd say, but in general, you could select some, let's say, you have all these grid points, and you could use them as, each of these grid points you could use as once a source and once a receiver, and then you can randomly reshuffle them and pick. We typically do about 20 to 30% of the points, and that's enough to really sample the entire domain. Because by using reciprocity, you could also use a receiver point as a source, right? So when you have the source receiver pair, basically the information is captured by one source and one receiver pair about this path, and then you don't need to sample this path again through by repeating this process with a different source and receiver pair. So George, I don't know if I answered your question, but it's hard to give a number here because it's tied to the velocity model heterogeneity.
Yeah, and I was thinking also you could do this also with pins or physics informed, no, DeepNet, sorry, DeepNet, physics informed.
Right.
Yeah, that would
Exactly.
be something for transfer learning, but that's why I was wondering.
Right.
Yeah,
right.
thank you.
Exactly.
Yeah.
Thank you, George, for mentioning that. Exactly, that's what we've been thinking to build this kind of solution so that it is independent of the velocity model. Hopefully, that's the hope. I know it's going to be challenging, but that's what we plan to do in the future. Of course, there are many avenues with pins. It's a very exciting field of research, and as George pointed, DeepNets could be a place where so our, let's say, model is tied to the velocity model, and therefore if you change the velocity model, you need to retrain your neural network. So that's what George was alluding to with DeepNet comment. Thank you, George. Okay, so that was the first work that we published, and then we have this book chapter that's coming up in March. It's already been accepted, and in this book chapter we talk about pins as the flexibility. We highlight the flexibility of pins in solving the iconal equation for different forms of the iconal equation. So previously I talked about the isotropic iconal equation, but actually the Earth is not isotropic, and seismologists have found many years ago that that seismic waves are subject to some other kind of phenomena such as anisotropy. They experience anisotropy as well. So one of the things that we did was to show how we can incorporate anisotropy in the pin framework. Now, I joke about this, that it took me 2 years during my graduate studies really to take an isotropic fast sweeping solver for the iconal equation and build the corresponding anisotropic one. So it took me 2 years, whereas with pins, it's just a matter of single lines. So essentially, you change the underlying partial differential equation, and the entire machinery remains the same, and you can get the solution. That's one of the very interesting features of pin, that it allows you this flexibility of adding more physics into the framework without having to change the algorithmic construction. So here you have the anisotropic iconal equation, which is corresponding to one form of anisotropy called tilted transversely isotropic medium, and you not only have a single parameter now that represents the velocity, but you have velocity variation with wave propagation direction, and typically it's represented with 4 different parameters that we have here. So what we do here is that we show that it again is able to beat the fast sweeping method in terms of the accuracy, and also now the more physics you add, the more time it takes to solve the using the fast sweeping method, and therefore pins get to shine more and more because essentially the cost for solving pins is not associated to your underlying PDE, but it's in the training process, and therefore more complex PDEs are the place where pins can beat fast sweeping method comprehensively, let's say. And we also showed, as in the previous example, that if you want to incorporate varying topography, which is the case when you're doing land seismic surveys, for example. If, for example, in mountainous regions, you have to model the topography really well, and therefore people use some sort of mathematical flattening or kind of other ways. For example, they use a finite element method to approximate the topography, whereas with pins, this is very flexible. You only train on points below the topography, and you only evaluate your model for points below the topography as well. So that's another flexibility that we talked about in this paper. So, in this book chapter that's going to appear in March. One more thing we mentioned in this. So one of the criticism with pins that we face when it comes to modeling is definitely that, for example, if you have a single source, that's not the case when you want to use pins, and that's where pins can be very costly. When you have multiple sources, you can accumulate the cost and compare with fast sweeping or fast marching method, and that's where pins can be more, let's say, advantageous to use. And therefore, we have also been doing some efforts in making pins computationally more efficient. And there have been efforts from the group of George and other people as well in making the PIN training process efficient. So one of the things we highlighted here is that is big because of the spectral bias of neural networks. Initially, the neural network is learning the low frequency features of your underlying solution, and therefore we do not use a lot of training points in the first phase. So we propose a two-phase training process where initially we just train with only let's say 5% of the total points, training points that we want to use, and build let's say a crude solution, which is very smooth. So what you see here are travel time contours emanating from the source located here. In red is the reference solution, and you see there is this local variation here because of the velocity model. Dashed black lines is the neural network or the PIN solution, which you see is highly inaccurate in this region because we use only very few training points in this region. And in blue is the fast sweeping solution, which of course uses all the grid points. So initially we get a solution that's worse than fast sweeping, but then in the phase 2 of this process, we introduce more points, and you could do this based on the places where you have, let's say, higher errors or residual, then you could introduce more points and you could do the training. So instead of training based on whatever selection of training points you want from the beginning, you can split this process and you could reduce some cost. So that's just a very, let's say, naive approach of reducing some cost associated with the PIN training process. Now I go to more interesting examples of using PIN. So the previous examples that I showed to you guys, those are the things that we already have solutions using conventional methods. Now I'll show you a couple of examples where there are some limitations with conventional methods, and we show that PINs is able to overcome those limitations, which is very interesting. So one of the things that we are interested in computing travel times, not only for the compressional waves or the P waves, but also for the shear waves, for waves generated by the shear motion. And this is important for many studies related to, specifically related to earthquake seismology and microseismic studies as well. But the problem with computing travel times for QSV or vertically polarized shear waves in anisotropic media is the presence of these triplication points where you have multiple ray paths crossing, and this leads to these triplications where the solution is unstable if you're trying to solve using conventional methods such as ray tracing. And therefore what people do is they use what is called as the weak anisotropy approximation. So they assume that the anisotropy is only weak, and that allows them to solve in the neighborhood of these triplication points because these triplications are not so pronounced there, and they're able to approximate the solution in this neighborhood of these points. And we showed in this extended abstract that we published or we presented at the EAG annual meeting last year, that with PINs, actually, you're able to approximate these solution close to these triplication points really well. So what you see in this image in the background is the wave field solution, because there is no way we could solve for arbitrary anisotropy in the medium using conventional techniques. So therefore rely on the wave field method. So we compute wave fields. That's what you see in the background. And overlaid on top in red is the PIN solution snapshot at t equal 0.5 seconds. And we show clearly that the PIN solution is highly accurate in approximating the propagating wave front here. So that's one interesting application of PINs where it is able to go beyond, let's say, what conventional methods could deliver. Another interesting example is when you have more complex physics, and that is when you have attenuation and isotropy. So, and people have found that, especially in heterogeneous reservoirs, you have not only have an isotropy, but attenuation associated with it as well. That is, you have wave absorption phenomenon as well. And the resulting PDE that comes from this is highly complicated. It results in a coupled system of equations. And you get actually two travel times. One is corresponding to the real part of the solution, and one is the imaginary part that tells you the absorption. So the real part tells you the phase of the propagating wave front, and the imaginary part tells you the absorption of the wave amplitude, right? So here is an example where we show that actually PINs is able to compute the solution again because you just plug in the PDE. In this case, it's a little more complicated PDE, but you have a coupled system of PDE here I haven't written it completely because it's a very complicated system of PDEs and very long, but you could refer to this EAG abstract to look at the entire PDE. And because there is actually no solution using conventional methods. So actually before using pins, we tried this problem using conventional method, which is the fast sweeping method, and we were not able to solve it, or we could solve it only for the case where the velocity model is homogeneous and using just an approximation based on the perturbation method. So that's how, let's say, inaccurate we were in that respect. And with pins, we were able to really overcome this challenge. And because there is no solution, so in order to verify the accuracy of our solution or our travel times here, what we do is we plug our travel time back into the PDE and try to extract the velocities that were used to train the model, and we compare them. We compare the retrieved velocities with the actual velocities, and here is the residual, which is highly accurate. And what we see here is some minor errors, which are in the order of 10 to the power minus 4 kilometers per second, which is absolutely negligible. So that's these two examples are really where for us pins shine compared to conventional methods where you cannot really solve this problem. So one of the points we made in our book chapter was that with pins actually put us on a much faster path to progress in, let's say, understanding how seismic waves behave in the Earth's subsurface, and especially in complicated media. And that is true with these examples.
I have a question here on this, because I think Raj, who is in the audience, has been working with another fellow from geophysics, and we had this issue of boundary conditions. So you have to do absorbing boundary conditions for the waves traveling around, and you have to implement them explicitly, because we found that we don't have to do anything.
Right. So in this case, George, there is no boundary condition because this is the Eikonal equation. This is not wave field. So
I see. You don't have. Yeah, it's first order problem. Yeah, just the time. Yeah.
Right. So yeah, later I will talk about wave field problem, and there, yes, we have to deal with the boundary properly. Okay. Yeah, but we can talk later about your work.
No, I thought, because I didn't see the equation, so I thought that you actually have full wave equations here. No, it's still the time Eikonal.
It's a static Hamilton-Jacobi equation. So another interesting feature, which I'll go over really quickly because I have to cover a lot of ground, is dealing with gaps in the velocity model. So conventional methods, one of the problem with them is that if you have missing velocity in some region, you cannot use them because they rely on what is called the upwinding method. So they basically construct solution in the increasing, let's say, in the characteristic direction. So if you have missing velocities somewhere or gaps in the velocity model, then essentially you cannot use conventional methods. So here we did some experiment for 1D velocity model. What you see in red is our 1D velocity model, which is very blocky in nature. And in green are the training points. So we train our, let's say, pin model using points here, and we assume that we really do not have the velocity information in this large region where we have this, rapid change in the velocity model. And then we use some training points here as well. And then once we have trained the model, we try to recover and see what it says or what it gives us in the region in between. So we see that it actually gives us some sort of average of the velocity that it was not seen. And therefore, you don't have to worry about missing velocity models, missing parts of your velocity model, and you could construct the solution because pins build global solutions where your travel times, if you just want to compute in this region, are not affected by what you're missing in between. So that's an interesting feature that we recently submitted to IEEE transaction in geoscience and remote sensing. So here is just a quick application of this where you have the source here, and this is the velocity model in kilometers per second, and you're missing the entire velocity information here in this region. And we just try to train the velocity model with points here in the circle or in this ring, and we are able to actually build the correct velocity model or recover the velocity model because the errors are extremely small in magnitude of 10 to the power minus 3 kilometers per second. Now we come to the part where we talk about wave field modeling very quickly. So we also, not only we worked on many different forms of the Eikonal equation, but we're also interested in solving for the wave fields. So what we do here is, instead of solving for wave fields in the time domain, we work in the frequency domain. So essentially what we have is what is called as the Helmholtz equation, which you see here. And this is used a lot in full waveform inversion, where you do waveform inversion per frequency. So you solve for different frequencies and you do waveform inversion with increasing frequencies, and you build solutions along the way. Here is the solution using a finite difference method for, I believe, a 5 Hertz wave field for this 2 scatter model. So we have a homogeneous model in the background, homogeneous velocity in the background, and we have 2 scatterers here. And this is the solution. Basically, you get the real part of the solution and the imaginary part of the solution. Now, if you naively apply pins to this problem, you would get something like this. The real part on the left, the imaginary part on the right, does not look at all similar to the correct solution. And this is because we have point source singularity again at the source location, for which we need to sample the source region densely with points, which of course adds to the computational cost of the whole process. Therefore, what we do is, instead of solving for the wave field itself, we solve for the scattered wave field. So we again divide the final solution, or U in this case, into 2 parts: U naught, which is the solution of a homogeneous medium. So this is the background wave field. And we solve for delta U, which is the scattered wave field. So this is called the Lippmann-Schwinger form of the Helmholtz equation. And what we get is now these scattered wave fields. That is what we solve for. And once you add this to the background wave field computed analytically, you get the desired solution. And we see here that there are large errors here in this region. I call them large compared to the Iconal equation, but in general scheme of things, it's pretty good. And this has been one avenue where we have been trying to improve pins, and it's been challenging, let's say. So this is one, let's say, area of active research where you want to approximate these solutions even more in more accurate manner. And the higher you go in terms of frequencies, this becomes even more challenging to use pins. And that's what our challenge has been, that if you work with high frequencies, let's say 50, 60 Hertz, then of course conventional methods are very expensive, but with pins, you struggle with, let's say, in terms of the computational speed of the algorithm. So that's an active area of research for us as well. One place where I'd like to highlight is we also worked on the anisotropic wave field modeling. So here what you see is model corresponding to anisotropic medium. Here is the velocity. Here are the anisotropic parameter, delta and epsilon, I believe in this case. And here is the wave field solution on the left, the real part of the wave field using a finite difference method. And here is the one using pins, and they look very similar, and there is no problem with the source that's placed here. Now, what if you place a source in the region where the medium is highly anisotropic? And what happens with the finite difference method is that you get a lot of numerical artifacts, and you can only solve it using finite difference methods by using very fine mesh, which results in a huge, let's say, increase in terms of computational cost, whereas with pins, it does not matter. And we see, as in the case of Iconal, that actually the challenge with pins is not how complicated your PDE, whether it's anisotropic or attenuating, whatever, but it's more about the underlying solution, how complex it is, and what kind of function you're trying to approximate with it. So in this case, really it overcomes a challenge that we observed with the finite difference method. Now I'll move to a few examples of inverse problems. The first one I'll talk about is seismic tomography. And seismic tomography has been actually used as a preeminent tool to illuminate the Earth's subsurface at many scales. So people have been looking at building, using seismic tomography to build velocity maps at the global scale, at the regional scale. Is what you see, I believe, for Southern California region or the United States. And people have also used it for the exploration scale, velocity model building, and in even smaller scales for using cross-hole tomography for studying smaller regions. And people have used it for many different applications. For example, monitoring carbon dioxide plumes and stuff. and in geotechnical site investigations as well. So again, what are the challenges with conventional methods in seismic tomography? So they suffer from a number of limitations, which we could address effectively with pins. And one of them is the need for a smoothing regularizer. So if you use something called what is popularly used as the adjoint state method, you get a lot of numerical artifacts that you see here. These are not, let's say, actual part of your gradient, of your wave-field or travel time gradient, but it's some artifact associated with the source locations. And typically the way people address this is by using some smoothing regularizer. So they smooth this domain, this area, so they use some kind of smoothing window, which results in a loss of resolution of the final solution. Another issue is the sensitivity to the initial model. And many a times you've seen that people start with different initial model, which means different initial velocity, and they converge to a very different velocity model. And sometimes those velocity models that they converge to are completely unrealistic. And that's one of the problem with conventional methods. And if you start with a homogeneous velocity model, it doesn't work because you need rays to dive and sample the medium. And therefore what gradient you use, for example, in surface tomography is also important. So that's another challenge. What initial model you use when you are doing seismic tomography. Another is if you have irregular topography, then the algorithmic complexity increases by a lot. And also, of course, when you want to use different hardwares, whether you want to use CPUs, GPUs, etc., then it's very difficult. You have to rewrite your codes in some cases, right? And therefore, we built a pin-based tomography algorithm that actually addresses all of these limitations very nicely. And how do you do that? So similar to our previous construction where we had this iconal solver based on this first network, which was supposed to predict travel times, given the source and receiver locations, essentially we do the same. So we have our first network, which takes source and receiver locations, or in this case, you can have points within the computational domain, and you're trying to predict travel times. And there is a second network which only takes points within the domain or training points within your computational domain and tries to predict the velocity at those locations. And they are simultaneously trained using a single loss function that is formed by 3 terms here. So let me go over these 3 terms. The first one is the data mismatch. So typically we have some receivers that record the observed travel times. And therefore we want to say that the predicted travel time by the first network should match, at least at these locations, the travel time that we observe. That's the data mismatch term. The second is the boundary condition. That is that at the source location, that is you have seismic source. In active seismic surveys, you already know your source location, so you can enforce this condition as well. And you can say that at these locations, your boundary condition should be honored. And finally, your underlying partial differential equation should also be honored, which is the iconal equation, and it combines the travel times at training points and also the velocity. So what happens is that you end up with, of course, you go through several training iterations and you need a number of different source locations. Once you train, you are able to predict travel times corresponding to each of those sources. So travel time fields corresponding to each of those sources, but also velocity using this network. Now, one thing you would note is why the velocity network does not have these additional inputs, which is the source and the source coordinates. And it's because velocity is independent of the source location, and therefore we don't need to input source location. No matter what the source location is, actually velocity is independent of it. So that's essentially what it is. And you could learn more about a few tricks that we do in order to, let's say, guide the solution towards, because it's a highly ill-posed problem, and there are many models that could satisfy satisfy all these conditions, but there are a few tricks that we use which are highlighted in this preprint that is available on arXiv, where we talk about this in more detail. So here's an example of cross-hole tomography, where we have this true model shown here, and we have some sources here, seismic sources here in one of the boreholes, and in the other one, for example, we have receivers. This is your initial model, which is, in this case, we don't choose an initial model. It's chosen because of the randomly initialized neural network. So that's what we have, really very far away from what we could expect from the velocity model of a typical Earth. And this is the inverted velocity model, which looks very similar to the true velocity model in terms of the, let's say, the smooth feature. And that's what we expect from the travel time tomography to give us. That is the macro velocity model. And then you could use full waveform inversion to really get these layers, these fine layers and these sharp variations in the velocity. So what we see here are a couple of profiles, velocity profiles taken at different x values. So you take different x values and you take this vertical profile and you compare here. In black is the true velocity model. So you see these local variations here, whereas in red is the inverted using travel time tomography based on pins. And it's able to capture this macro features, which is essentially what we use travel time tomography for, to build a good initial model for subsequent full waveform inversion in case your, let's say, goal is to build a high resolution velocity model. The other thing I'll talk about is hypocentral localization. That's another kind of inverse problem which is useful in earthquake seismology studies and also in microseismic monitoring, where we don't know the source location and we are interested in finding the location of the source given the velocity model. And this is because of my interest in induced seismicity studies. And very quickly, I'll go over this, where induced seismicity has been a problem because of many of the industrial operations, specifically related to the energy industry. And it has been observed in pretty much everywhere in the world. So whether and people in Oklahoma would know this because of wastewater injection. People in Korea would know this because of the enhanced geothermal system there. And people in Groningen, for example, would know this because of the Groningen gas field. And this is a nice, let's say, graph where it shows different regions of the world and where there have been earthquakes, and sometimes very large earthquakes. For example, this one in China, it was magnitude 7.9 because of a dam and water impoundment in the dam. So there have been several, let's say, events in the recent past, and there have been, let's say, of increasing in terms of frequency in different parts of the world. So here is a graph showing events of magnitude larger than 3 in central US. And what you see here is from 1973 to 2008, it had only 855 larger than magnitude 3 earthquakes, whereas between 2009 and 2016, there were almost 3 times more magnitude 3 or larger events. And you see this hockey stick pattern here, which is related to many of the industrial activities, and particularly in Oklahoma because of the wastewater injection. And it has resulted in huge social unrest and outcry in different parts of the world. And typically what people use to, let's say, manage the risk or hazard associated with induced seismicity is what is called as traffic light system. So these operators have to go through some protocol where they have to do continuous microseismic monitoring of their operations. And what traffic light system says is that if there is an event in the vicinity of the operation that has magnitude larger than a preset threshold, then basically you have to be careful, which is, let's say, this amber light. And if it exceeds the next threshold, then basically you have to halt the operation and wait for certain time period, or there is a protocol when you can restart the operation. And there have been a lot of problems in different parts of the world, including Groningen, where the operators had to really close the field, or the plan is to close the field, I believe, this year later, which will result in a lot of, let's say, not only financial costs, but also there are other aspects. For example, there is less, let's say, tolerance for many of these industrial activities in these regions. And therefore, managing these operations safely is really a priority. And we've been working on doing this where we could use traffic light system, for example, relies on how you could identify these events in real time and also locate this event. So here's a study where this is basically data-driven method where we detect these events in groaning and in real time. If you want to read more about this, you could refer to this article in Sensors. But what I want to highlight today is where we use pins to locate these events in pretty much near real time. So the idea here is you can have this neural network, but now you don't have the source location. So what do? You have some, let's say, training points, and you have the data recorded on the surface where you have this microseismic monitoring network. And you essentially say that, okay, I want to have travel time field where it satisfies not only the data that I have received, but also the PD in the domain. This is slightly different than the tomography problem, because in that case, we know the location. In this case, we don't have the location. So how do we find the location? Is once you train your neural network, you build the travel time map, and you get something like this. And then you say, okay, where is the minimum travel time in this field? And that's the location of my source. So that's how pins can also allow you to solve the hypocenter localization problem. And once you have solved it for one source, you essentially could use, again, transfer learning for new sources, and it essentially gives you a solution in a matter of few seconds. This is an example of our work from the Ottaway velocity model. Ottaway is probably the largest CO2 sequestration field in Australia. And what we do is we have this velocity model, and we say that, okay, we have these 3 different events that are induced there, and we have the travel time peaks only on the surface at a number of receivers. And can we use pins really to go back and predict where they came from? And what you see in the bottom plot is the true location in black, and the predicted location in this, I don't know, light green color using entire array. But what happens mostly is that you cannot pick at all receivers because of noise, for example, and stuff. So that's what we simulate. So we only use 35% of the receivers, and the red marker shows the location that is really with only a few receivers in this area. And that's where I think pins shine, because you have the PDE to overcome the ill-posedness of this problem when you have only a few receivers, because it not only tries to satisfy the solution at these locations where you have the travel time available, but also it has the PDE to really constrain the solution better.
Umair, can you tell us where the receivers are and how many?
Yeah. So the receiver, so typically in geophysics, we have this constraint that we can only record on the surface. So in this case, we have these receivers here, and we use about 300 receivers in the full, let's say, array. Whereas when we are using this irregular receiver setup, so we randomly remove 65% of the receivers. So we use 30%, 35%, which is about, let's say, 100 receivers, which are randomly located, which typically is the scenario that you get in a microseismic monitoring setup.
And the simulation is 3D or 2D? I mean,
this one is 2D. This one is 2D.
Oh, okay.
And this is pretty new. This is less than a week old.
Okay.
And we are actively working on this to make this, let's say, more robust and try it for different configurations.
But the receivers would be deployed on the surface, right? In an array on the surface, in a
3D setup. Yeah.
So you do in the 3D sense, yeah. So you do have that. So okay. And then the only thing you need is the different layers, right? The structure of the layers, the property, which you have, because that's a well.
Yeah, you could build it using some active seismic surveys, and typically these operators have done some studies in the region to build a velocity model.
Right.
So they could do this, but there is also an associated problem which I don't show today, and that's what is really a big challenge in seismology, is joint hypocenter and velocity inversion. That is, simultaneously you invert for the velocity and the locations.
Yes.
As you can imagine, this is a highly ill-posed problem, and this is what we are trying to use pins to address. Yeah. But so far, it's a work in progress, and I don't have any slides to share that today.
Sure.
All right, thank you, George. So I'll quickly close this. I know I'll be running out of time, and there'll be a few minutes for question and answer. So what I've talked about so far is mainly related to industrial operations. I'll quickly show some examples of global scale travel time modeling. So you could also use pins to do to solve some of the challenges associated with people were working on earthquake seismology at the global scale. So we're working with the GLAD M25 velocity model that was built by the group at Princeton, and you have this velocity model given for the global Earth model up to the core mental boundary, about 2,900 kilometers. And essentially, what we are trying to do is we are trying to take points on the surface as receivers, because that's where you would record earthquakes, and points in the domain as sources. And we're building, let's say, a surrogate model where once you have trained, you're able to then predict travel time instantly from any point in the domain. So any location where you can have an earthquake, you can compute travel time to any receiver point. So in this case, we only work with the US array, which has more than 2,000 receivers, and we build a surrogate model. And then we predict our travel times, which we try to analyze how good this travel time is by plugging it back into the Eikonal equation and recovering the velocity. And this is our recovered velocity with the travel times that we obtained. And this is the residual, which shows pretty good accuracy for most parts of the globe at depth of 24 kilometers, except for a few locations where the velocity is changing sharply. That was at depth 24 kilometers. Here is, let's say, a vertical slice at a particular latitude and longitude, and we can see this residual blown up by 100 times here, and it's pretty small, to be honest. It's about 1% maximum, as we see here in terms of velocity. So this is something that we presented at the AGU fall meeting last month. So just to quickly summarize. So I've tried to demonstrate the efficacy of PINs on a wide area of applications on problems pertaining to computational seismology, and I've tried to highlight where PINs have made a contribution in addressing some of the long-standing challenges. There's still more challenges that need to be addressed, and that's what we are actively working on. One of it is if you have sharp heterogeneities in the velocity model, that's where I think we need more work, and how we could make PINs computationally more efficient and the solution more accurate. Hyperparameter selection, as with all, let's say, machine learning problems, is an issue. Multi-value travel times. So oftentimes you have not only one solution from a source to receiver, but multiple solutions. How could you solve for those multiple travel times? That's also an issue. And also, we are thinking about actively using data and physics-driven, combining them to further, let's say, use the potential of both techniques to benefit from it. I would like to acknowledge my, let's say, collaborators, Tariq Al Khalifa from KAUS mainly, and we have working on this topic for almost 2.5 years. And there've been other collaborators with Hassan as well, and Jean from University of Grenoble Alps, and others who've worked with us. And thank you for your attention. If you're interested in more details of these different topics, then you could go to my, let's say, YouTube channel, and you will find several recorded talks that you could look at for details. And I'll be happy to answer a few questions, whatever time permits. Thank you, everyone, for your attention.
Thank you, Umair.
Thank you, Professor Umair. Questions for the speaker?
Raj, do you have any questions?
Yes, Professor. Thanks, Umair, for your talk. I have a couple of questions from the travel time tomography which you showed. So how did you compensate for the amplitude there? Because wave field is like dealing with both the travel time and amplitude. So
Right. So just to clarify, so in that problem we're using, this is travel time tomography. So you only use the kinematics of the wave field. We don't use the amplitudes, right? So if you want to use the amplitude as well, then you would want to use the wave equation. So in this case, we're using only the Eikonal equation, which gives you the travel times only.
So that amplitude was just some sort of the Gaussian pulse or something like?
No, there is no amplitude information. So what you're doing here is you are, so you have first arrival travel times that are observed. So this is just the phase of the propagating wavefront. We don't take the amplitude into account. So when you are comparing with your observations, typically what's done is you have an initial step of picking the travel times on your recorded wave fields, and that's what you compare with the predicted Eikonal solution. So the tomography problem typically or the travel time tomography problem does not take the amplitude into account. That's, I believe you are working on the wave, using the wave equation.
Yes, but one of the collaborators from geophysics department, it's acoustic wave equations primarily. So
right. I saw a preprint. I believe this is with Chris Huber.
Yes,
Chris
Chris
Huber,
Huber, yeah.
Right.
because that was the big problem of scaling. Actually, matching the amplitude was the big problem.
It is. Yeah, it is. That's definitely a challenge.
But we non-dimensionalized the wave equation and did not impose any boundary conditions. So it's just put some data inside the domain, and it worked perfectly. So
yeah, and yeah, so that would probably be challenging when you're working with let's say real data, I believe.
Yes. He generated some data from SpecFem, like so that's but he used the attenuation also in that. So that's but yeah, so having data in domain always help for the velocity model and amplitudes.
Right, and that's what we are limited, right? In the domain, we don't have observations. Typically, it costs a lot to get observations when you want to drill wells, for example, and put receivers there.
Yeah. So I had a question. You showed a model for the Marmushi where you did the travel time tomography. How long it took to converge that model? Like how big was it?
So that was for the travel time modeling part.
Yeah.
Yes, well, the more heterogeneous, that's what I identified as one of the challenge with pins, is how the heterogeneity. If you have a heterogeneous velocity model, then you can build very smooth solutions really fast, but then compensating for those local variations is not easy, right?
Yes.
It takes a lot of time, and computationally, that's an outstanding challenge, I'd say.
Did you try XPin, Umair? Did you try XPin?
No, George.
Yeah, the XPin would work here. I don't know, Ameya, if Ameya is here. Also, the adaptive activation function. We showed that in a paper we haven't released yet for shocks in multi-dimensions, that you really need to use adaptive activation functions for discontinuous solutions, and then it works fine. Actually, we solve Riemann problems like that. But there's a paper. It's called Kronecker Neural Networks, KNN, in neurocomputing, that Ameya published. I don't know. Maybe he's not here today, but
yes, George, I'm here.
Okay, because Ameya, I was thinking about the high frequency problem that you actually solve. Remember the
yes
high frequency Helmholtz equation, exactly what Umair. Yeah.
Yes.
So maybe you can tell Umair the equation you solved and how did you, because Pindi will not converge at all for that case.
Okay. Yeah, sure. I can talk to Umair later through email.
But it's basically an adaptive activation function of. He has different forms, but in this one, he puts a little bit of sinusoidal perturbations superimposed on the hyperbolic tangent. And he gives a inductive bias to go away from the spectral bias from where of the neural network. So that's basically the idea.
Right.
And it worked well for the Helmholtz equation for high frequencies, which wouldn't, I think if you give Umair that, the high frequency Helmholtz equation, that, that example.
Yes, yeah. I can send him an example. Yeah, I'll send him a paper direct.
Yeah, so thank you, George, for pointing that. So I haven't talked in detail about the different things that we use to make the solution, let's say, converge. And adaptive activation function is something we have been using throughout in all of those examples that I showed. And I have been looking at Ameya's work, and I guess you call it RowdyNet.
The Rowdy, the Rowdy. So
yes,
if you use that,
yes.
Yeah. So I haven't used that here, but that's what I wanted to do as well. So it's been in my plans. Absolutely, yeah. You're right. Thank you. So I'll talk to Umair.
Yeah, sure. I'll send you the paper. Yes.
The XPin also will be very appropriate because you have these layers, right? So you know where they are a priori. In our case, we have to chase them, and that's the preprint that Ameya will submit soon. But In your case, the discontinuities or the heterogeneities are known a priori, so you can actually prearrange your the domain decomposition. Yeah.
That's a good point. Yeah, sure. I'll definitely look at it. Thank you, George.
So thank you, Professor Umair. So let's move to our second talk. Our second talk is from one of the members of the Crunch group, Qian Zhang. And Qian, can you try sharing your screen?
Yeah, I'm here. Yeah. Moment. Can you see the screen now?
Yeah.
Yes.
Okay. Is this the only a single one slider in the screen and say JAX features and applications?
Yes.
Okay, let's not present her.
I'd like to introduce you. So
Yeah,
he's a first-year student in the Crunch group, and he would be presenting about the features and application of the JAX. Thank you.
Okay, thank you very much. Today, I will just give a very brief introduction to the JAX. The software package may be useful to our research in deep learning and scientific computation. I will basically talk about its features and some very elementary applications. Well, I can assure you it's a very easy thing, and there is no mathematical formula. So relax, there's no tensor, and good afternoon, everyone. First, let's say what's JAX. From the Google's GitHub page, it says that JAX is an autograde and XLA brought together for high-performance machine learning research. Well, the autograde is, well, a simple Python AD system, auto differentiation system. And this is designed for CPU only, so you cannot expect it to work on a very large scale deep learning system because it just works on the traditional CPU architecture. And the XLA is accelerated linear algebra. This is designed to power the TensorFlow's codes to accelerate it on the GPUs. So Google brought them together to design the so-called JAX. And well, to be short, it's a lightweight open source machine learning library. To say it's lightweight, well, typically JAX package is about 200 to 300 megabytes, while the TensorFlow or PyTorch is at least 2 to 3 gigabytes. So it's just with a very small size. However, it can power almost everything you want to do: auto differentiation, vectorization, well, just vectorization, XLA acceleration. Optimizers also included in that. So it's a full-powered machine learning library. And the last thing is very important. It is developed and maintained by Google. So you can expect its quality is guaranteed. And also widely used in the DeepMind. The AlphaFold is also written in JAX. So it is fully powered with every features you may want to conduct research. And then we will just say why JAX, especially in our group. First, our research, like Pain and DeepNet, is highly dependent on the auto differentiation system. Well, differentiation we want is kind of different from the typical deep learning community. Well, in most cases, we want to train a model y equals to f, where p is the parameters and x is the input. For the typical deep learning community, they just want a scalar y as loss and the p as the parameters. That's what they want. But in our case, we need to find the connection between the y and x that are real physical quantities. That means the y is a vector and x, of course, also vectors. So in that case, we need to find the differentiation about y and the x. That's a y prime. And then we will take y prime, y, or even high order different derivatives of y into the loss functions. So the auto differentiation system in our research is very important. And the second, the auto differentiation system should be very flexible in that case. If a package just like PyTorch or TensorFlow, they are designed for the traditional deep learning, but it may not serve us well. So it must be very flexible, just like AutoGrad. Here, the TensorFlow 2 or PyTorch, they may not have some features that we need. I will discuss later. And also should be simple to write. Here I have to say kinds of the offset that like TensorFlow 1. TensorFlow 1 is a really bad, well, software package. You will write hundreds of lines of code, which can be easily implemented with other software packages. And finally, it should be efficient. The autograde I've just mentioned before, it's very elegant and simple, but it cannot be efficient because it's designed for the CPU only. So JAX has solved all these problems. It is very flexible, it's simple to write, and very efficient as well, which can be useful in our research. Let's see some very important features of JAX. The first is NumPy-like API, which means you may not need to change your code a lot to get yourself into the JAX. And second one is the auto differentiation. Like I just said before, the auto differentiation system of JAX is very flexible and very easy to write, and most importantly, it's efficient because it has a XLA acceleration. The third one is the vectorization. I will show you a very interesting example later to see how it may power our research. The XLA acceleration, or just the acceleration for the speed, as you can see. And this one is pure functions. I will take a little time to discuss about these pure functions because this kind of programming style can be very helpful to when your code base growing up to thousands of lines, and it will be help you to maintain and develop the code. Finally, JAX is fully battery included, which means you can have everything you want in a single package. But it also has a very active ecosystem powered by the DeepMind. So you can find reinforcement learning, graph neural networks, optimizers, and anything else you may want to have. So let's just start from the NumPy-like API. Well, just like you can see, the left side is just the JAX APIs, and the right side is NumPy APIs. They are almost identical. You just need to import JAX.NumPy as JNP and add a J before every NP dot. So the other things are almost the same, except for the random number. The implementation of random number generator is a little different from NumPy. I will not dig into that because you can just find it on the official document. But as you can see here, you can from the linear algebra operations like the matrix multiplication or instance summation, or even the FFT, you can do almost everything you can do with NumPy in the JAX with a minimum modification to your code, just like replace NumPy with JNP. So that's quite easy for you to do that. The next part is auto differentiation. This one is a bit tricky because you need to change your mind to some opinion. The auto differentiation in JAX is different from the TensorFlow in the PyTorch. In JAX, the auto differentiation is based on the functions. As you can see here, I define the function and take gradient on the function. Not like in the TensorFlow or PyTorch, I define a function, I invoke a forward pass to compute the function value of a certain input, and then I differentiate from the input to the from the output to the input. They are different. I call the TensorFlow or the PyTorch like the variable-based differentiation, but for in the JAX, it's a function-based differentiation. So you can define your functions and define your differentiation before you run your code. That can be easier for you to debug. And also the code can be concise, and in some cases, I will show you later. This is a very simple example. You just define a square function and you take gradient of it, and you put an input at the gradient functions and get its output. Well, for this function, you will easily get a 6 at the output values. And also it can deal with the partial derivatives. There are two implementations you can do to deal with the partial derivatives. The first one is you do it with a multiple input. In this case, you take two arguments to this function z. It takes x and y. It's the summation of x squared and y cubed. For the partial derivatives on the x part, you just need to grade it. It will, by default, take gradients on the first argument. It will not take derivatives on the y. But if you need to take derivatives on the y, you just need to parse an argument like argnum equals to 1. Well, that means the x, the argnum is 0. In computer science, the first one is almost 0. And when you try to differentiate on the second argument, you need to specify that argnum is 1. And you will get the two different partial derivatives. The first is the partial derivatives on the x, second is on the y. And then you specify the value you want to take derivatives and substitute them into these two partial derivatives functions. Here I use a prefix called fn. That's need to remind you that the auto differentiation system in the JAX is function based. It will do the gradient on the functions, not on the values. That's very important. Just when you try to switch your code into the JAX, that's the key part. The next one is to, well, use an array as input. It's a single input. like this, you take the index 0 and index 1, just like here, argument 0 and argument 1. The two functions are all, the same. The only difference that you just need to pass an array as an input instead of pass two individual variables into the functions. And all the other things are the same. You just need to kind of specify what you want. Here, the gradient function, when it's applied on the array input, it will compute the derivatives on all the elements of the input. When you pass two variables, like for the array of length 2, which means it contains two elements in this input vector, the grade will also give you a vector of length 2. The first is partial z partial x, and the second is partial z partial y. So you need to take it out by using the index as well. Here I have to say that lambda is just a syntax. Don't take this too seriously. That means you have defined anonymous functions, and you give it a name later. Oh, sorry. And you can also do high order differentiation as well. Here I will use the second way to show you. I already have the partial z partial x functions, and I can still take the second derivatives of partial z partial x. That means I have second derivatives on the x part. Similarly, if I change the 0 to 1, it will be first take the partial z to the partial x, then take the derivatives with partial y. So that's quite easy and to compose it like you do calculus. It's very simple. The second one is the
Qian, can I ask a question?
Yes, please.
Have you compared the cost for TensorFlow differentiation of the AD versus this? Have you compared yourself?
I have used the JAX in my research, and I think their speed is almost the same.
Okay, no better, no faster.
For
higher order derivatives.
In high order differentiation, there is no such problem. In my research, I do NS equations. I think that's already a high order differentiations. Their performance are almost the same. And on the internet, I've searched for GitHub Stack Overflow. They say that the speed of JAX is almost the same with the TensorFlow. Although there may be some difference. In some cases, TensorFlow may outplace JAX, or JAX may outplace TensorFlow. But in the general case, their speed are similar to each other, and there will be a same scale. So not very clear difference.
Okay.
Yeah. Next part is the vectorization. And here I will introduce you with another one called VMAP. Well, this one is very important feature because, well, in this case, you are just trying to take derivatives with a scalar with respect to another input. The problem is when you try to take derivatives, sometimes you need to deal with a bunch of data. In that case, it would be kinds of the take derivatives of vector to another vector. In that case, we can use the VMAP to map the functions to the vectors with vectorization, essentially. Well, to give a very brief introduction, that in Python itself, it gives you a high order function named map. It will map a function to a list. Or it's very naive. It's simply a syntax trigger for the for loop. Well, to some extent, it can also use the multiple CPU, but it's not designed for GPU or numerical computation. So the VMAP is redesigned to parallel your code with vectorization. It's similar to the effects to the original map in the Python, but the implementation is very efficient. It can be very useful when you, like I just said, you take gradient. You have defined you have defined a function fz, and you want to, like for instance, you not single input. You may have several inputs, and you want to have several derivatives as well. Well, in that case, you don't want to do a for loop. In that case, it can be very not efficient in that case. So you can use VMAP to broadcast your function to the vectors, and it will take derivatives at the same time, just like this visualization. It will compute all these derivatives at the same time by the vectorization, because CPU itself or even GPU is parallel. Another thing is you can do, well, in this case, of course, as a toy case, you can easily have the matrix vector product by simply add. But when it comes to some very complicated operations, you do not have kind of the batch operation like the matrix vector product. You may find VMAP very helpful because you can just write a very naive case for a single example, and you can just use VMAP to broadcast it to several vectors like this. Of course, we all know how to use the matrix vector product, but when you do some very tricky things like the differentiation in some places in DeepNet, I will show you later, it can be very helpful to simplify your code, and also can make something seems to be impossible to become possible by this VMAP operation. And the last killer feature is the XLS acceleration. It's very simple to use. In fact, you can, as long as the functions you want to parallel or accelerate is pure, I will discuss this later, it will accelerate your code in a very dramatic speed. In my personal experience, if you play it with a toy case like a simple regression, it can accelerate code to 10 to 100 times. But if you want to do on the GPU with my case, it also can have you about 10 times faster. So the JIT is very efficient. Of course, the JIT is also kind of the sign to say that I will compile this part of function into a static graph. It has already been a kind of the controversial that the static graph is it's the comparison between static graph and the dynamic graph may be controversial. People will say that dynamic graph is easy to debug, while the static graph is more efficient. In JAX, they can be combined. First, when you try to develop your code, write your code, you want to debug, you want to become, easy to find what's problem in your code, you can just comment out this JIT, and you simply write this function. When you think that your function is correctly written and you want to accelerate it, just add some JIT, and it will compile into your code into a static graph and accelerate your operations. Of course, you can see that there will be no placeholder, no session. So let's outplace TensorFlow 1. Of course, you don't need to write everything in a very long list. Like I said, placeholder for this variable, placeholder for that variable, and the session don't run. And you don't need to write that anymore. You just write in a Pythonic way and add JIT to make it into a static graph. That makes everything easier. And then I will talk something not so deeply related to the JAX itself, but also it's something that JAX will push you to do. That's pure functions. JAX features is expressing and composing the transformations of numerical programs. The expressing and composing means that they are pure functions can do. It is designed to work with these pure functions. The pure functions is that when you put into the same results, it will give you the same output. If you put same input, it will result in same output, and there is no side effects. Like when there is no mutation of local static variables, for instance, you cannot change the variables you input, and you cannot change the global variables, that's the non-local variables, and there is no input, no output. Like this one's impure, and this function is pure. JAX can accelerate the pure functions to a very high speed. And the pure functions itself is also very effective in maintaining and develop the code, because it will first make your code very concise. Next part is it will make your program structure very clear, because in the pure functions, as you can see before, your data is separated from your logic. Your operation on the data is not related to the data itself. So when you change your data, you will easily see how it will change the outputs. And when you want to debug, you just need to make sure that your logic is not easily modified by data itself. So it's very easy for you to maintain the complex programs. And another thing is that your functions are the composition of simple functions. So when you really need to change the function or change the feature of your code, you can simply modify the small part, the atom functions, the simple functions. And you do not need to change the structure to reflect a very large scale. And so it's very easy for you to debug and develop. And when I do my research, I've taken over a code base where everything is written in a single class. And it will be very hard to modify, because as you can see, when you try to add some new features to your code, you have to pass new parameters into the class. And then you need to change the methods of the class for every functions. So it can be very disastrous, especially when you have a 500 to 600 lines of code in a single file. But if you have a functional style, everything can be very easy. As long as your first design is not bad, you can just simply change the well, the entry for the content of the function you need to change, and everything will work as you want. So you don't need to change everything in a rapidly or will make everything into a mess. So I think that pure function style can be helpful when you're trying to do something large in hundreds of lines of code base. It will help you a lot. And the last feature, oh, sorry, not the last feature, it's a something overview about its API. This part is about the JAX is kind of factory included. You can have everything you want in the package. The first is JAX.numpy. The JAX.numpy array is the data structure that can store your data, and it can be placed on the device you want, typically in our case on GPU. Of course, when you do debug, you can put it on the CPU, and for Google themselves, they can put their array on TPU. And in other JAX.numpy, they have many other functions, just as I said before, the FFT or other kinds of different numbers or anything else. There are functions applied on the JAX array. And the next one is great VMap JIT. There are 3 essential features of JAX, just like I said before. And finally, it has also the optimizers. Well, in deep learning part, it may be very easy for you to write the model, how it will give the forward pass, how it will apply on the variables, but it's very difficult for you to write optimizers. So JAX also included optimizers. So you do not need to find many other difficult part in writing optimizers by yourself. Of course, it still has some kinds of the flex optext package that also provide optimizers implementation. So you can do them in a quite easy way, and as long as you like it. It also has a very powerful ecosystem if you do not just want to use JAX itself. The first called tracks is provided by Google as well. It's a high-level APIs ranging from like loading data to create training tasks. It's even more powerful than, well, TensorFlow to some extent, because it can just abstract everything in a single class. Although I do not like this style of code, they can do such powerful things. And also provide pre-trained models like transformer. So when you just want to do something like transfer learning, or you just want to use the pre-trained model on your own data set or task, it may be helpful to you. The next part called flags or haiku, they are kinds of low-level functional APIs, and there will be no over-abstraction like tracks. Flags and haiku are provided by Google and DeepMind respectively. I think they use these two as their basic package for them to develop. And the optext and optimizers with friendly API for you to use. The JAX optimizers, the vanilla JAX optimizers a bit verbose when you try to use them. The optext can give you a simple interface if you need to. And finally are some domain-specific packages like Relax, JAX, and Giraffe. They can use for reinforcement learning, deep learning code testing, and the graph neural networks as well. So you can see that JAX can do almost everything you want to do. For the features there, they can fight with the TensorFlow and the PyTorch. So if you want to change to JAX, there will be not many feature problems for you. And I will show you to the applications part in our research. The first is a very simple regression model. I will provide a full and a detailed explanation on lines by lines. It may take some time. And then the next two are just two very naive examples. Oh, sorry, the third one is not naive. Second one is a naive examples. It's a 2-point boundary value problem. And I will show you how to write flux functions in pings. And finally, the NS equations, and I will show you how to deal with the very complicated physical equations with JAX to write the derivatives. Well, for the regression part, let's just do it lines by lines. It can be tedious for expertise like you, but just to make everything complete, I will try to make that as slow as possible. So the first part is to import modules. You need to import everything you need, like JAX, JAX.numpy, and NumPy itself, of course. You want to generate data if you need it. And the JAX, you need the JIT that will enable the XLA acceleration. And then VMap, you need it to do the automated vectorization. And the value in the grid, it will compute the gradient and compute the value as well. It's very useful in computing loss functions. And you need optimizers to train your model. Here I will use a very simple multiple MLP model to do a regression. And here are just some auxiliary packages. First, you generate the data. It's just kind of the well, you generate random data and you want to train the square functions, approximate the square functions. Now we come to the detailed part of how to use JAX to write and train the model. First, like I said before, JAX encourages and even pushes you to use a pure function style. So in JAX, the models are not single model self. The way the model applies on the variables and the parameters of the model are separated. So you see, the first is called net FN. That means how the model will be applied to the data you input to it. This is just an MLP with activation value. So I think that's quite trivial for most of you. And the second part is to initialize the model parameters. And then here I use Gaussian normal and initialize the parameters. And finally, I initialize the parameters by single quality functions. So when you try to train the model, it will actually be the two parts. The first is you take the parameters into the net FN, the apply functions, and this one will apply to the data you input. And the second part is use the results to do backward and auto differentiation. And I will show you how to do this. Oh, yeah, here. The first is define the optimizer. Like I just said before, the optimizer provided by vanilla JAX is a bit verbose, but it's not very difficult, just a little more things to write. And next is how to define loss functions and update function. They can be used to train your model. The update means that for a single epoch or single batch, depending on how large the batch size is. And here is the logic. First, you unpack the data you have the input. And data is, oh, sorry, yeah, that's it, the data. I input the data as an argument and I unpack the data. And then I define the loss functions. The first is, well, in the loss function, I want to get the output of the neural network. So I use the FN as a kind of the abbreviation. Of course, you can just use this function to replace the FN, but this way make the code clearer. The way is that you first define you first define a network function with two inputs, the parameters and the data. And then you define a function with the input, single argument input. And then you vectorize the function to the data part. Well, if you do not use the VMAP, it will compute the loss of a single sample. But if you use the VMAP part, it will vectorize your function to the all the vectors, all the elements of the input vectors, and you will have the loss of the entire batch. So that's the way how JAX to parallel your code and optimize it. In TensorFlow, it will basically be well, you apply the model onto an input X and you take gradient of Y to X. In that case, you may see it seems to be easier, but it hides some tricky part, and it may be very difficult for you to modify the something underlier. So I think this one is superior to TensorFlow. Although for this very toy model, it can be a little not go on with your instinct, but it's very helpful when you deal with complex models. And then you have the loss functions. Then you take gradient of the loss functions and use the gradients to update your to get to the optimizer to update your parameters. And this is how the logic goes on. And then you have the new optimizer state in the loss functions, the loss values, and you print the loss values or do any visualization you want, and pass the optimizer state to the next update function. So in the entire loop, you will you do not maintain a single class or a single object called model. You just pass the optimizer state to the function to obtain a new optimizer state. That's pure functional. This function does not change anything outside of the itself, so it can be JIT to be accelerated with JAX. And it will be easy for you to debug as well because the logic is separated from your data. So when you want to kind of replicate some bugs or results you are interested in, you just need to pass your inputs again, and there won't be any, you'll expect the same results. It will be very easy for you to locate and deal with the bugs. That's for the single regression part. If you can—
Qian, I have a question
Yes?
here. So if you were to write this in TensorFlow or PyTorch,
Yeah.
Which one of the three will be the shortest code, the most compact?
Well, if you want to use for this problem, the most compact code, I would suggest kinds of TensorFlow 2 in the Keras style.
Okay.
Yeah. After all, this entire code base is less than 100 lines. But if you go to something real problems like Pings or DeepNet, it can save you a lot. And this is the how I write the update function for 2-point boundary value problems. This function. It's very toy, of course. The solution is JAX. And I will show you how to write it. The first is I write the as well the simple function, and then I take derivatives for 2 times, and then vectorize it onto the input. Here is the residual points, and then I have the equation. And the equation from the equation I compute the physics laws. And for the boundary equation, it's just the same, but it's a simply forward pass. So everything are very simple here, and I combine the laws together and train it as these last 5 lines are identical with this one. So you can replicate your code base very easily. And this is the results. Ping is very powerful in data sampling, as is well known. So when you try to do the 2-point boundary value problem, the tricky part is you need to take derivatives for twice. You want a high order differentiation. When you do it in TensorFlow, you will find that you will need to do the tape, and you will have twice annotation. And I will show you it later in another case. It will be very helpful to just write a single. It will make your code base clear in a single logic layer, so it will not be many annotations and make your code base a lot of mess. And here is how I write. Sorry, I have to say that since the code base of this equation is very long in that case, I will just write some really essential part. For the 2-point boundary value problem, the essential part is to write your equation laws, and that's these several lines. As you can see, the equation laws I comment here. And for the NS equations, I have these lines as the.
So these are the Navier-Stokes equations for those of.
Yes, exactly.
I have to say that because not everybody does fluids.
Oh yeah, okay, sure. This is Navier-Stokes equations. The last one is the mass equation, the conservation law of the mass, and these two are the momentum equation on x, y directions, the conservation law for the momentum on 2 directions. And well, if you want to just know about Navier-Stokes equations, you just ignore the x in the ellipsis, and there will be the s equations. These lines should equal to 0 if it satisfies the NS equations. So the way I compute it is almost the same as before. I just need to define the ping functions and then take the several components of it. The u will be the first, v the second, and the p will be third. And then I take derivatives, I take gradient. Oh, here I have to say that u, v, p are functions, not variables. And take gradient on the u as the grade u, and the first is on the take derivative on the t, so that'll be the first component of the gradient u. And the similar things is also for the ux, uy, or everything else. And here, if you want to do higher differentiation for the u and v, you just need to take gradient for the ux and the vx or everything else again. That's quite straightforward for you because they are also functions. So functions are easily to produce differentiation as a function as well. And finally, I compose these functions by the lambda representations. And these 3 are also functions. But these 3 functions, when it applies to input, the situation is that their results should be 0. But of course, there won't be 0, so we will train them on these 3 equations. These are functions. And finally, all I need to do is to, well, like just replace the Fn with EQ1 and bmap it on the kinds of the residual points and take the L2 loss on it. So that's the way I do this on the NS equations. This is JAX code, and this is TensorFlow code. So you will find it many verbal things here. You need to write the tape. And you even need to remember which tape you need to do, because when you try to take differentiations, you cannot do T2 on it because it's not computer within that one. And in that case, for the T2, you cannot write T1 because it's not recorded the gradient information. So it can be a lot of memory burden for the code writers. And also there will be longer for you to write everything else. So I think that when you try to deal with high order differentiations, unless you just like NS equations, the JAX will bring a clear code style and easy for you to maintain. And another thing is called batch gradients. It's quite typical for the DeepNet, I think. I do not do research directly about DeepNet. I heard it from Sichen, and he has struggled with deal with these batch gradients for a long time. And I have to say this implementation within TensorFlow is very genius. It's used the own features and all the APIs provided by TensorFlow 2 to do this feature. It means that in DeepNet, you want to kind of apply a function to several points, and you will get the value on the several points. Am I right, Professor? I will take that. I think that's right. And when you do these gradients, you will take the gradients from the y1 to x1, y2 to x2, y3 to x3, blah, blah, to the yn to xn. And in that case, you cannot just do the TF dot gradient, because in that case, it will give you a Jacobian. But in fact, you just want the y1 to x1, y2 to x2. We will make the computational cost from the on to on squared. That's unbearable in the computation. So in that case, we have to introduce kinds of the dummy weights. You use the dummy weights and you put it into the differentiation part and take differentiate for twice to get the results like the y prime. And in that case, you have a very nasty code base, in fact, and you will find it's very hard to do the very tricky modification to your code. The ansem is very hard to write. In fact, you have to transpose, you have to do many things to make the code work. Of course, it's very genius because TensorFlow does not provide you with very advanced techniques, but we can do it in a very clear way in JAX. That can do the same thing, just like this, and everything was simple. You just need to define the forward function for a single case. In that case, you pass by a single example, and you map it onto the vector, and then you get what you want. Of course, the y prime, you just need to map it. It may seem to be verbose because the lambda representation, but in fact, they are just the compositional functions. It's quite easy for you to manage your code. They are very straightforward. You just need to remember that, okay, this trunk v function is just the vectorized version of the forward functions, and you want to apply to the branch, and then you use trunk functions and do the same vectorization. So here are just some kinds of this, you specify on which axis you do the map. And all the other things are just the syntax verbose. You just write it, it works. But the essential part is these two. So everything can be made much more easier than this kinds of batch gradients. And you will have the results in a very straightforward way, especially for you taking the prime of y. You just write it in one line, vmap twice, take gradient once. When you need to do the second order of y, of course, it's very simple as well. You just need to take gradient again. You add 4 letters. But in that case, you have to write 2 more gradient tape. And it will be even harder for you to remember which tape I should use. So it seems JAX to be very helpful in many ways, but I have to claim that Google didn't pay me, and I have to say something drawbacks about JAX itself. First, it's relatively new library, so the performance may be unstable. Like George has asked me before, JAX is cannot outperform TensorFlow everywhere, and it may suffer some performance problems compared with TensorFlow 2 in some cases. But in my research, their performance are similar to each other. But it may be a problem for some research cases. I cannot say that for sure. And second is that currently the community is relatively small, just compare with TensorFlow and PyTorch, because they're really big monsters in that case. You can see people from everywhere. As long as they do deep learning, they will use these two packages. JAX is kinds of the small guys and young guys. It does not have many support from the community. And also like some legacy code. So you will, when you try to implement something, you possibly need to implement it by yourself. Of course, they can also be well explained as kinds of it is not technical debt. When you try to implement something new, you will not be constrained by the past code. It's just you need to rewrite everything. It may be good for you in some cases. I find some problems in my old code base by rewriting it. So when you're trying to do something like refactor code, you may find some problems and you may solve it. And also there are another problems in the paradigm for the JAX is not familiar to the current deep learning community because it's function-based auto differentiation. In JAX, in TensorFlow, you compute the variables and you take the gradient of the variables with respect to the input of the neural network. This is a variable to variable, but in JAX, it's just function to function. You take the gradient of the function and then you do computation like VMAP or JIT or anything else. Also, there's something good is that it's encouraging the functional programming style. It will be helpful when your code base is very large. It will make your modification easier and also maybe helpful to your debugging. But first, you have to overcome the unfamiliar paradigm. And here is the little summary. First, using JAX means that you can write in dynamic, write in static. That means you write your code in a simple way, but your code speed is very fast, just like TensorFlow. And the second part is very flexible, well, very simple. You can write the very flexible to differentiation while your code base can be very simple because you just need to write a single batch, single sample, and you use VMAP and it will be a batch function. So everything can be very easy in that way. And for debug, since it encourages functional programming style, the debug things can be easy because same input, the same output, you can just use bisection or anything else to find out where the problem is. And also it's promising. Since it's used and maintained by DeepMind and Google, you can expect that there will be many surprising results later, especially from DeepMind, just like AlphaFold. And you can see that since they can do this, of course, when you do something in research, you can also do that as well. The problem is it's not mature. So when you try to kind of start a new project, you may want to use the JAX because everything is new. There will be not many burden on you to rewrite the code or something else. But if you are in a good development in your project, after 3 or 4 months, you have a very large code base and you think everything is going on well, then JAX may not suit you because you need to change everything. That can be very expensive for your time. So my suggestion is that if you are doing something toy, simple, or you're starting something new, brand new, I mean, TensorFlow cannot satisfy your demands. JAX welcomes you, of course. But if you are going on well, everything is going on well, you can just use what you are using now. And you can, of course, try JAX to some extent. But full buy-in may be a little too far for you. So that's all. And I hope that it will be helpful to your research. And good afternoon, and thank you very much, everyone. Thank you.
Thank you, Qian. That was great. It was very informative.
Maybe we can have a discussion with Raj, from Raj, to get a first response from Raj, who is a programming guru.
Yeah. I just from making this PPT and I changed my code base into the JAX. I discussed with him for a lot of times, and he helped me a lot. Thank him as well.
No, I want Raj to tell us what he thinks also.
So about the JAX. So I think yeah, means it is very easy to write the code in this framework if you are starting new project. But as Qian said, but there are like along with that, I prefer using Flax. Actually, Flax has some better APIs for optimizer and all those. But it is a good paradigm to explore. I think I didn't explore much. I just know about this, just need to know basis. But one thing is there are some problem with running these codes on GPUs. Actually, there are a lot of issues which I've found. But I think if I can fix the similarity, then it will not be the issue. So. But I think it means it's a good to explore this paradigm. So there are a lot of things embedded, and if you know Python, you don't have to learn this. It is very similar to NumPy and Python. So yeah.
But I can share some of my experience with JAX.
Yeah, sure.
So
yes, Adar.
Yeah, so we had an issue, one of the first papers that we worked on.
Turn on your camera so that people will see your new face. So they will
Okay,
see.
I'll stop my sharing.
I'll try. One sec. So what we tried to do is incorporate some time-dependent process in the loss function. And this was apparently a lot of work because as TensorFlow 2 works, they kind of, they need to assign placeholders first for everything before they, maybe you can, oh, now you can see.
Yeah.
Cool. So basically, I'll say it again. So what we had is in the loss function, we had the time marching process. And as TensorFlow works, they first assign placeholders. So they had to assign a placeholder for the entire time marching element, which is batch size times time steps times nx times ny, which was a huge tensor to assign and crashed our computers all the time. We approached the guys from Google that worked on JAX. They created some collab to show us how to do it using JAX. And basically the idea is that JAX knows how to free the information within the batch size. Okay, so essentially the placeholder was just the time step times nx times ny, and each batch size was freed after every calculation. Eventually, we did not use it. We found a better implementation for that, but this might be like a use case where you will want to use JAX. Yeah.
Thanks for anybody else who has experience with JAX wants to say something or ask questions.
Yes, can I have 10 minutes? I prepared something.
Sure.
In addition to
yes, we do have time. Yeah.
Yeah, sure. Okay, so thanks. Next talk, Qian, like some functionality JAX supports for training and computing deep neural net is very useful for us. Like this is a kind of a complementary to Qian's talk, since like I talked to him like before this seminar, and I realized not many people in our group know this functionality from TensorFlow. So I'd like to give a very brief introduction, like tutorial, like 10 minutes tutorial to this like batch Jacobian, which is very helpful for the deep net training and computing. And yeah, so now this functionality is supported by like this the latest version of TensorFlow. So basically, like Qian already mentioned, that if we were dealing with a scalar function, then there's no trouble, because we simply for TensorFlow 1 we use tf dot gradients. For TensorFlow 2 we use this tape gradient to take the gradients with respect to the input, which may be like we have a batch. So the input dimension is this is a scalar function, like a loss function. So the input dimension is 7 times 7 by 1. The output dimension is 4. For each data point, we have a 1 output, so it's 7 by 1. And so the gradient dimension is also 7 by 1, which is very simple. But for if we have vector functions, suppose like what we have in like the output of the trunk function in DeepNet, which is like higher, which is multi-dimensional, then we have problems using this original TF dot gradients or tape dot gradients, since the output, again, the input is still, the dimension of the input is still 7 by 1, but the output, since for each data, each training point, we have a multi-dimension where the dimension is 10, then the output dimension is 7 by 10, and the expected gradient dimension should be also 7 by 10, since we have only the input of the trunk net is, the dimension of the input of the trunk net is 1. But using this tape dot gradient or TF dot gradient, we have a summation over all element, all derivatives of the elements with respect to the same input. So that's the problem. However, like TensorFlow has like two functions to deal with this issue. One is Jacobian, tape Jacobian, and the other one is tape batch Jacobian. So for Jacobians, it computes the Jacobian. So the output dimension is 7 by 10, and the input dimension is 7 by 1. So the Jacobian, of course, is 7, 10, 7, 1, since we are computing the derivative of each element of the output with respect to each element of the input. So that's how Jacobian, so tape, a gradient tape Jacobian works. Since we're not interested in this, we're interested in the expected dimension of the gradient should be 7 by 10. So like we do it batch wise. That's where this tape batch Jacobian shines. So it assumes that the first dimension of the input and output are consistent. They are consistent. So we're computing like 1 by 10, the derivative of a 1 by 10 output to the derivative to with respect to the input, which is dimension is also 1. So after the functionality, the usage of this function is very similar. Tape gradient, you just replace the gradient with batch Jacobian or Jacobian. Now we have the output of this gradient function is 7 by 10 by 1. Since this one is corresponding to this one, so if we have the trunk net, the input of trunk net is no longer x, is something x1 z t. We have a multiple inputs. Then for example, is here it is 2. Then the gradient here is also 2, so which is perfect for our purpose. And for higher order derivative, it works like tape gradients. So instead of tape gradients, we use tape batch Jacobian. And here, since the shape is we have a more dimension for this matrix, we just squeeze, delete the last one, since the last one is 1. And then the output is, this is second order derivative, the output is 7 by 10, because we miss 1 here, because here I also squeeze it out. So this 7 by 10. There's another way to do this Jacobian, batch Jacobian in TensorFlow. But I don't recommend this for TensorFlow 2. If you are using TensorFlow 1 or using, you install TensorFlow 2, but you're using TensorFlow.compile.v1, which is a version 1, the compatible version 1, then you can use this Jacobian and batch Jacobian from this file, this path. But if you are TensorFlow 2, you're using the tape.gradient, if you're using eager mode and graph mode at the same time, then I don't recommend that. I'll explain further. So if you are using this Jacobian and batch Jacobian, their functionalities are the same as the previous one. And you simply, the function, the gradient function is simplified. You simply use Jacobian and you have the same output. And for batch Jacobian, you just use batch Jacobian. You don't need to use tape anymore in either TensorFlow 1 or TensorFlow 2. But if you're using this one, if you don't want to use tape, then you have to pay something. No free lunch. You have to pay something. So this is the reason why I don't recommend this batch Jacobian and Jacobian function, from those two paths here in TensorFlow 2, because like TensorFlow has bug for this one. And okay, I forgot to mention that the cost for usage of this Jacobian without the tape is that we can only do this in graph mode, meaning that we have to decorate the function with tf.function. So it cannot be run in eager mode, which means, which is hard for our to tune, to debug. So it works. So the graph mode in TensorFlow 2 works very similar to TensorFlow 1. So which is nothing we're familiar with that. But for this batch Jacobian, we have some bugs. It's not a problem with this design, or my code is a problem with TensorFlow. So if you change the source code, so the source code, this one in this path, you change this 0 to this one, so they have the same physics meaning. Then everything works fine. So this is not problem. It's not our problem. It's a problem with TensorFlow. This is, but if you're using TensorFlow 2, if you are using this tape thing to compute the gradients, higher order gradient, higher order derivatives, then I recommend directly using tape.Jacobian and tape.batch Jacobian. So for TensorFlow 1, surprisingly, this functionality is also supported by TensorFlow 1. So here I use the latest version of TensorFlow 1, and they're all the same. Here, but how we compute the gradient is different. In TensorFlow 1, we simply call tf.gradients to compute the gradient, like first order, higher order gradients. And then, yeah, of course, because we have a scale vector function, and if you're still using tf.gradients, then we have troubles. But you can directly use, you can do it in the TensorFlow 2 fashion, but using TensorFlow 1. So this tf.gradient tape is also supported in TensorFlow 1. So the logic of like the structure of the codes are the same. And this another way is also supported in TensorFlow 1, but this time it's more friendly supported. So again, we don't need to write gradient tape if you don't like that. And since this environment is TensorFlow 1, we don't have eager mode, we only have graph mode, so we don't need to use a tf function to decorate this function to make it a graph mode. Then again, Jacobian from this those paths could do the job. And for batch Jacobian, you don't need to change the source code this time. For TensorFlow 1, you don't need to change the source code to make it right. So you can directly use batch Jacobian, and we have the same similar output dimension for this gradient computation. So for TensorFlow 1, TensorFlow 2, for graph mode or eager mode, you can always use this Jacobian and batch Jacobian for DeepNet computation, but you have to take care of it. So the reference is this website from TensorFlow is called Advanced Auto Differentiation, and yeah, you may want to try it if you're working on DeepNet. That's it. Thank you.
I have a very quick question. You have shown an example of second order boundary value problem. Have you tried it for like higher order boundary value problem, like fourth order, like a Timoshenko beam type of thing, where there are different boundary conditions?
Well, I was just using this one as kind of the demonstration of the JAX code. Of course, you can write a high order differentiation or other types of the, well, boundary conditions. You can use kinds of first order derivatives as boundary condition or everything else. You just need to write a function to accelerate, to write functions to take gradient as well. I didn't write that just because it's a toy case, so I didn't put many efforts to make it very advanced. You can also write that in that way. That's easy.
All right, thank you.
Thank you very much.
I think,
hi.
Go ahead, Nuri, go ahead. Yeah.
Hi, Zhong. I have a question regarding what you introduced just now. So yeah, I see that you introduced the batch Jacobian and Jacobian. Yeah, both of them. So does that mean that whether my understanding is right, is that, for example, the 7, 10, 7, 1, the dimension, so the batch Jacobian essentially picks the diagonal elements along the two axes from the with size 7. Is that right?
Yes.
Okay. So have you ever heard of any function in PyTorch that does the same thing as the batch Jacobian? Because I think that one is pretty important. And because I think that PyTorch, the automatic differentiation is maybe the worst among all the like TensorFlow 1, 2, and PyTorch?
Sorry, no, I'm not very familiar with PyTorch, but sure, I can take a look at it. You mean the functions supported by PyTorch, which has the same functionalities as batch Jacobian and Jacobian?
Yeah, same functionality as the batch Jacobian. I didn't find that.
Maybe Raj knows.
There is in PyTorch the functional Jacobian actually. So you may try that. Torch has a function called functional Jacobian.
Yeah, that Jacobian, it looks like it takes
because
it functions similarly to the Jacobian, right? The full Jacobian. For example, 2D to 2D, then it becomes 4D.
Yes.
May I ask?
But we can hack it to work like a TensorFlow. It's not a big deal. So.
Yeah, is it a like true problem you met, like in your project? So if you think it is a like serious problem, I can check it out. I think
I remember. I remember that I once encountered something where I need to use the function similar to batch Jacobian, but what I can find is just the full Jacobian and also some like autograd, and none of them work very well. I can definitely include some for loop, but that's low efficiency.
Yeah, that's good.
Yeah.
Minlang is also using. Minlang, are you using PyTorch, right?
Yes, but I met that problem before, but I don't think there is a function in PyTorch can calculate the batch Jacobian. So in this sense, I think TensorFlow is much more efficient.
Yeah,
I just Googled it, so by the way.
Yeah, I also Googled, but I didn't find anything. So, okay. Yeah, so I think this problem is especially annoying sometimes when I want to implement a DeepNet, because we have the BET dot product sometimes, and we have lots of different dimensions. And sometimes you need to take derivatives for multiple axes.
This batch Jacobian thing is not a problem when we're working on pins, but when we started,
no problem for pins, absolutely.
Right. When we start to work on DeepNet, it becomes a trouble. Right.
Okay. Yeah. Thank you.
No problem.
I think Qian, thanks for initiating. This is a good discussion. I don't know if anybody else has anything to add, but I think the message here from Qian is that if you want to work for DeepMind, you have to know JAX. So.
Hey, George.
Yes, Romulo, yes.
Oh, hey, this is Romulo. So I just wanted to add something very quickly. So I was just exploring the JAX documentation a few days ago, and I saw something interesting, which is called MPI for JAX.
Oh.
So I saw a different approach to what we do with like data parallel code, which is like basically computing the gradients locally, then you perform some kind of collective operation to averaging them and then performing the updates. So those guys, they claim to be able to actually differentiate through MPI operations. So you can like perform the collective operations like a multi-host and internode operations, and then you can create the computational graph for the collective operations. I'm not really sure where we could apply it right now, but it's just something I thought we could like keep in mind for.
No, we have a data parallel code that Raj is running, the turbulent code. Yeah.
Oh yes, I know, but that's what I'm telling. That's different from data parallel. Yeah, you're actually performing the collective operation and differentiating through the collective operation. You're not doing something like the data parallel approach, like computing the gradients locally and then doing whatever collective operation you do. I'm not sure if I was clear about that, but like if anyone had any interest, you can just check. Or look for MPI for JAX. You'll see an example right at the beginning of the page. So it seemed very nice to me. Like,
so Romulo, that is exactly what we are doing in the data parallel. We are computing the loss locally, taking the gradient and average it out. So
yes, but you're not performing the collective operation and then differentiating the collective operation itself. That's what I'm talking about. That's different from the data parallel approach.
Oh, in JAX.
Yes, in JAX. That's something in JAX. Like, I know JAX is new and not mature, as Ken showed us, and this is a library like complementing JAX functional capabilities, but maybe it could be useful in the future if you want to do something involving collective operations and want to differentiate through them. just something I thought could be useful. Not now, not for data parallel code, but
Oh, okay. So it's a different algorithm.
yeah, for different algorithm.
So, but yeah. So the what we are doing in data parallel, like this computing the loss, taking the gradient locally and averaging it out. That's it.
Exactly.
But the problem is that when you communicate, like in XPin type of code, you can't.
XPin or CPin, yeah.
You can't pass the tensor across the node. That is the problem. So you have to convert into the NumPy array. Then you pass to the node and then you compute again on the tensor. So that is some sort of API I was searching. So I wrote my own locally for that. So means that is the problem with the Horoward and exactly the problem with the TensorFlow also. You can't communicate through tensors. That's it.
Yeah.
So that is
you have to convert them to NumPy and then you communicate and convert back to a tensor.
Because unless graph is evaluated, your tensor is not initialized.
Yeah.
So when you get the value, you have to detach the tensor from the graph. Then you cannot hook back it. So that is the problem actually. So we raised this issue with AMD Leopold. So Leopold suggested some alternatives, but I'm yet to explore that. So
okay. But like, if you have time, just take a look at the MPI for JAX, maybe.
Definitely. Yeah, but the data parallel approach is pretty much conventional, whether it is implemented in Torch, PyTorch, whether it is TensorFlow, whether it is in Horowitz. So
thank you, everyone. With that, we come to an end to this week's seminar. Have a great weekend. Be safe and enjoy the winters. Thank you.
Bye-bye.